This example starts with a single function, 10x cubed minus 3x squared plus 8, all over the square root of 25x to the 6th plus x to the 4th plus 2, a complicated function. And the thing about this function is that it has two different limits in the different directions of infinity. So the limit as x goes to infinity, which is part A, is going to be different from the limit as x goes to negative infinity, which is part B. And this aspect of limits at infinity is one of the most challenging aspects of the beginning part of the entire course. It's very easy to get tripped up over the subtle aspects of this example that we're about to work. So let's work through it and be very careful. Okay, so for part A, we have the limit as x goes to positive infinity of that function. The key here is to divide everything by the largest power in the denominator. What that means is to find the largest power. This only applies to x, so we have x to the 6th there. But it's not really x to the 6th, it's actually square root of x to the 6th. So when I say the largest power in the denominator, I mean the square root of x to the 6th. And then we want to divide everything by that. So what we'll do is we'll multiply the top by 1 over the square root of x to the 6th, square root of x to the 6th, and we'll multiply the bottom also by square root of 1 over x to the 6th. And you can see there, we're just multiplying by 1, right? This whole thing just equals 1, so we're mathematically sound. So the limit as x goes to positive infinity is the easier case of the two, because then we don't have to worry about absolute values or any of that. So let's just rewrite here, because we're going to positive infinity, let's rewrite square root of x to the 6th as x cubed. Where did that come from? Well, square root of x is x to the 1/2. So I'm writing this as x to the 6th times 1/2, essentially, and that's how we're getting x cubed. We'll have to think more about that step as we go to negative infinity. So I'm just going to replace this 1 over x to the 6th here with 1 over x cubed. Okay, so now we can rewrite this limit as x goes to infinity. I'm going to distribute this 1 over x cubed all the way through to everything, so we have simply 10 because the x cubes cancel out, minus 3 over x plus 8 over x cubed up top. Down below, I'm going to combine this radical, this big radical, rad 25x to the 6th and all that, with radical x to the 6th on the bottom. So that's going to give us the rad of, well, let's see, 25x to the 6th divided by x to the 6th will give us just 25 here. Plus, and then we have what? X to the 4th over x to the 6th is 1 over x squared, and plus 2 over x to the 6th. So now that we're ready to evaluate our limit, all these terms with a constant on the top and x on the bottom go to 0. Right? That's the wonderful thing about this method. Look at all that. So we're evaluating the limit there. So what we're really left with here is 10 over rad 25. Okay, now for the challenging part. For part B, we'll let x go to negative infinity for the same function. All right, we start off the same, divide everything by the largest power in the denominator. So once again, we're multiplying the numerator and the denominator by 1 over square root of x to the 6th, and down in the denominator as well, 1 over square root of x to the 6th. Okay, now for the details. The square root of x to the 6th is actually the square root of x squared cubed. Right? That's another way of writing this, and we can do that. That's legit with the properties of exponents. But the square root of x squared is actually the absolute value of x. So we have absolute value of x cubed. And this makes a difference as we go off to negative infinity. Why? Well, here's our fact about absolute value of x. Absolute value of x equals x anytime x is greater than or equal to 0. That's why we didn't care about it in part A. But anytime x is less than 0, you replace x with negative x when you go to evaluate an absolute value. This is simply a more rigorous definition of the absolute value. If you're not convinced that it works, try it with a couple numbers. Try it with 17 and negative 17. It works out. So since we're going to negative infinity here in this function, or in this limit, we need to replace absolute value of x with negative x. Right? And that's the real kicker. So the thing to remember here is that if you're evaluating the limit as x goes to negative infinity of f of x, you replace that absolute value of x with negative x. So let's get back to work on this example now that we know all this stuff about absolute values and negative infinity. So up top, instead of writing 1 over x to the 6th, I'm going to write that as 1 over absolute value of x cubed. But now we replace absolute value of x with negative x. So this is actually 1 over negative x cubed. So I'll put in here negative x cubed. And because this is odd, that negative stays in. If it were something like negative x to the 4th, it wouldn't matter. And a lot of examples are like that. But this one does matter. In the denominator, however, I'm just going to leave this as square root of x to the 6th and combine it under this radical here in our main term in the denominator. Okay, so let's get down to business here. Let's evaluate this thing. So this becomes the limit as x goes to negative infinity. Okay, so we distribute this 1 over negative x cubed. That gives us negative 10. Make that plus 3 over x. Won't matter, that term will drop out anyway. Minus 8 over x cubed. That will drop out too. All over the square root of, and then now it's the same as in part A. 25 plus 1 over x squared plus 2 over x to the 6th. Okay, we have done the heavy lifting. So if you can understand that fact about the absolute values and all that, you're in good shape. If not, it might take a couple times of looking at this to deeply understand how this works. Again, it's one of the more challenging aspects of the course. Right, so all these terms go to 0 as we go to evaluate this limit. All the terms with x in the denominator drop out. What are we left with? We have negative 10 over 5, which is negative 2. Okay, so there we are. 2 different limits in 2 different directions. Let's take a quick look at this in Desmos, just to get more of an intuitive feel for what's happening here with this function. Okay, so here we are in Desmos. The function itself is in red there, and that would be a very challenging function to graph without Desmos, though we do graph functions like this later in the course. So the function is red, and then I have drawn in the 2 horizontal asymptotes or limits at infinity at y equals 2 and y equals negative 2. And you can see that indeed the function is approaching those 2 limits in the 2 different directions. So I mentioned horizontal asymptotes. We oftentimes call these kinds of limits horizontal asymptotes, which is just a shorthand for saying limits at infinity.